So this was the picture that there are these two isotherms, one temperature T2 and T1. So you start with some point, you move along this isotherm, so that's an isothermal transformation. Then you do an adiabatic transformation, then another isotherm, and then you go back to, it has to be, go back to your initial point. And in this process you absorb an amount of heat which is Q2, you release an amount of heat which is Q1, and if W is the work done, total work done by the system for this entire process, then W is equal to Q2 minus Q1, and then you know that the efficiency is just 1 minus Q1 by Q2. So then I said that you can prove these properties, that if W equal to if W is greater than 0, then necessarily Q1 is greater than 0, which implies if both W and Q1 are positive, then Q2 is just W plus Q1. Q2 is equal to W plus Q1. That's also greater than 0. If the battery runs out, somehow it makes this noise. And then there is this Carnot's theorem that let me just write it down. If you want me to show how to prove it, I can do it, but I think it's a standard proof that's given in Fermi and any book on thermodynamics. So it says no engine operating between two temperatures, operating between, okay, there is an operating here. Between two given temperatures is more efficient than between two given temperatures is more efficient than a Carnot engine. Also, okay, so symbolically here you represent this Carnot engine by something like this, that this is temperature T2, this is temperature T1. So you absorb an amount of heat Q2 this way, you release an amount of heat Q1, and this system delivers an amount of work W to the external world. Okay, so that's one thing. And secondly, all reversible engines working between, you can, okay, so sorry, this one is T1. All reversible engines working between these two temperatures, T2 and T1, or between two given temperatures, all reversible engines working between them have the same efficiency, which is given by 1 minus Q1 by Q2. And this allows you to define the absolute scale of temperature, which I will probably not do. It's a straightforward derivation. Is there something that you want me to work out, or I just move on to Clausius inequality? Like, is it something, especially the teachers, like, are there particular features that you find difficult to convey that you would like me to do, or it's there's nothing such? Okay, so then I move to this Clausius inequality. So that says Clausius. So it says that you consider some cyclic transformation for which throughout which the temperature is well defined. Okay, so for any cyclic transformation, Clausius's inequality says that over the whole cycle of the transformation, this d cross q by t is less than equal to 0, where d cross q is the heat absorbed by the system. Okay. So it says that for any cyclic transformation, for any by the way, this is right, if I put an apostrophe, but this is the part of the name, but for some reason in books they drop this s, which I don't know why. We were taught that it should be there because it's not making it plural and so on. I don't know why it's on. Anyways, for any cyclic transformation, if d cross q by t, this quantity, heat absorbed, differential of the heat absorbed divided by the temperature taken over the whole cycle is less than equal to 0, where this equality holds if the cycle is a reversible one, if it's a reversible one, and this one if the cycle is irreversible. Like again, the proof is also quite straightforward. It's given in any standard textbook, and the way you prove it is to show that if d cross q by t, this integral is greater than 0, then you violate one of the you violate the second law of thermodynamics, and therefore it has to be less than equal to 0. Yeah,
so just one little bit.
Yeah, sure.
Acha.
Oh, acha.
When you do this by breaking it into a mesh and cancelling it out, but Pipard and Etke point out that it may not exist in the states in between. You are breaking it up into a mesh, the full cycle. So they do it using Max Planck's version of thermodynamics directly instead of using Carnot.
Yeah, I vaguely remember having read it in my college days, but now I don't remember the proof. Yeah, this from Cambridge University.
Yeah, this also follows the same thing.
Actually, I remember that for everything else we followed Szymanski, but for this particular proof, we were told that we should read this one, and therefore we all went to the library and got it Xeroxed. So I had the Xerox copy of me of just those pages, but later on I had the book. Downloading was not possible that way. Yeah, okay, so maybe one should look up this. It's called Pipard. I thought Pipard, no? Pipard. Pipard. Yeah.
I once went to book fair and inquired about the price. Guy who is a Brit, he said Pipard, so I said.
Oh, acha. Somehow we were told it's Pipard. Anyway, so I think he was from Cambridge University, if I'm not. He was a professor in Cambridge University. Okay, so I'm skipping the proof, right? I mean, you will find it, it's pretty straightforward. There is no, but the importance of Clausius's inequality is in, it lies in the following fact that it allows you to derive a state function, namely entropy, a very important state function, namely entropy. So let me do that part, and it actually follows directly from applying this inequality to a cyclic process. Well, actually the equality. So let me just do it. Let me see how Fermi does it, because this mesh thing probably Fermi also does the same way. Yeah, Fermi also does the same way, breaking it up into small bits. And so for this thing, what we should do is that So consider a cycle in which you go from one state A to B along a path which is reversible, and you come back to A along another path which is also reversible. Oh, sorry, you do it this way, okay. Yeah, how to do it. I think it says, yeah. Now I apply the Clausius inequality or equality for this cyclic process. So that says that actually for a reversible path I don't even need to put this arrow. Okay. So that says that d cross q by t taken over the whole cycle is equal to 0. So this path is reversible, this path is reversible, and therefore this is a cyclic process which is reversible. Now what I can do is that I can break up this into this path. I go from A to B along path 1, d cross q by t plus, I have to now go back, so I go back to A along path 2, d cross q by t equal to 0. But now what I can do is that I can bring this to the other side, and what I will get is this. But this path 2 being a reversible process, what I can do is I can absorb this sign and make this into an integral that runs from A to B along path 2. Right? So this right hand side is nothing but I am going from A to B along path 2. Why does it make this continuous? Huh? Battery problem or? No, okay. No, it doesn't seem to be a battery. The red light is not on. It's probably I'm doing something irreversible. I don't. Probably reversible. Okay, so what I did was I just absorbed this sign and made this integral into one that runs from A to B along path 2. But what this tells me is that now I have a quantity d cross q by t that simply doesn't depend on the path that I take to go from A to B. If I evaluate it along path A, the value that I get is going to be equal to the value that I get if I evaluate it along path 2. And therefore, this quantity A to B d cross q by t must be a function that depends on just the endpoints, because if I go along path A, I get the same value as I get if I go along path 2 and 3 and 4 and 5. Actually 1, 2, 3 and infinity probably, I don't know. So then it says that this should be, so this should be a quantity that is a state function that depends, well actually this is a change in a quantity that depends on only on A and B, only on A and B, the endpoints. So this allows one to define what is known as an entropy of any state with respect to some reference state, let's call it O. So this will be given by this integral of d cross q by t, but then I can evaluate this integral along like any path of my choice, like anything that I choose to take to go from my reference state to state A. And what I can do is that I can decide to measure my entropy with respect to this reference state, because this definition doesn't allow me to or it leaves me with an arbitrariness in defining the zero of the entropy. So what I can do is that I can decide to measure entropy with respect to an arbitrary reference state, and so this SO will go away, and it just tells me that entropy of a state is just the change of d cross q by t measured along any path that I choose to go there from the reference state, and the reference state is defined to have an entropy which is equal to 0, and this of course will automatically allow me to define the change in entropy in the change in entropy between two states A and B. It's just d cross q by t, like evaluated along any reversible path. Sorry, one should remember that I can evaluate it along like any path from O to A so long as the path is reversible, because I use that property that the path is reversible. So the entropy, the difference in entropy between two states A and B is just given by d cross q by t, evaluated along any reversible path of my convenience that I choose to take to go from A to B. Then there is another with that definition of entropy.
In the morning you mentioned the second law of thermodynamics. Usually it is given in this language. You cannot do this, you cannot do that. It consists of negative statements, things which are forbidden. From there, how do we get a positive result? There exists a state-dependent quantity. Qualitatively, how does it happen?
I would not say there exists. Maybe a good way to say is that it allows one to define one such function. It doesn't tell me that this is the function. It is a
one is good enough. But I'm just trying to see how it happens that purely negative statement has led to something concrete. You are saying at least one. That's good enough. How come it has happened?
No, because by I am making negative statements, so I am forbidding certain things to happen, and therefore some other things are happening in that sense probably, which is entropy. I don't know. This is the way it is done. That actually, like eventually, when one does statistical mechanics, that's what one does. That only those transformations are possible for which, let's say, if d cross q is equal to, I'll show it in a minute, only those transformations are possible for which the entropy can only increase. So that's a fallout of those negative statements, that these processes are not possible simply because for those the entropy doesn't increase, it decreases. I don't know whether it answers you, but this is just to, not entirely, like even I am also not convinced that it is the answer, but it is a answer and a possible answer.
The proof as given by Picard and all these people is somewhat contrary since they put in a small engine between these and finally end up.
Actually, all these things tell you that one has to go beyond thermodynamics. This is just not letting you. It's kind of like, as you said, you make a number of convoluted. You take up a number of convoluted. So construct something such that things work out. And it's primarily because it was just a phenomenological subject, like based on some experiments. So you just try to give a logical structure to your observations. Okay, so the next thing is to show that for an arbitrary transformation, and this will arbitrary transformation, it says if you take if there is an arbitrary transformation that takes you from A to B, it doesn't have to be reversible for any arbitrary transformation. Suppose it is irreversible and so on. So this is just less than equal to SB minus SA, where the equality holds if the transformation is reversible. So that we just saw that if the transformation is reversible, then SB minus SA is indeed equal to A to B d cross q by t. But if the path is not a reversible path for an like arbitrary transformation, the change that is going to take place, I mean this integral a to b evaluated along d cross q by t is less than equal to sb minus sa. So please understand that the right hand side is completely independent of how you go from A to B. It's just a function, it's just a difference of the values of the entropy at the end point and at the initial point. It doesn't care how do you go from A to B. So this thing is completely independent of how you go from A to B, while this quantity is by its very construction depends on the path that you take from to go.
And then we are relegating it and saying that whatever be the point path, reversible, irreversible in A and B, the difference is given by SB, point function.
Yeah, that's it.
How they introduce this quantity from the second law, dq by t, just after?
No, just from second law you don't get all this. You need also Clausius inequality. Clausius inequality tells you that if you consider a cyclic transformation and consider this integral d cross q by t taken along the whole cycle, then this one, the way I proved it, that if you consider a cyclic transformation, it doesn't have to be reversible or irreversible. Just for a cyclic transformation, this quantity is less than equal to 0. If it's a cyclic and reversible, it's equal to 0. If it's cyclic but not reversible, irreversible, it's less than 0. Then what I did was I used the reversible version of this equality that said d cross q by t whole cycle is equal to 0. Then I constructed that cycle where what I do is that this is a reversible path and that is also a reversible path. For the whole cycle, d cross q by t is equal to 0, but then I broke it up into contribution in going along this path and contribution in coming back along this path. But since this path is reversible, I just changed the sign, and therefore I get that the value of d cross q by t evaluated along this path is equal to the value along this path, and so on. All these reversible paths are going to give me the same contribution for d cross q by t integral, and therefore it must be that d cross q by t integral is a quantity that doesn't depend on which reversible path that I choose to go from A to B. It's the same for all, and therefore this d cross q by t must be a quantity that depends only on the endpoints. That's the only way in which you can get a contribution that doesn't depend on the path, and this lets me define this entropy the way it is done here.
This Clausius inequality cannot any more input beyond the second law.
No, yeah, it's a consequence of the second law. Yeah, second law. Yeah, it's just the way you prove it is you just show that if d cross q by t integral is greater than 0, you violate one of the second law. Yes. Achha, now I show that for an arbitrary transformation d cross q by t, this thing is, so this is done in the following way, that let's consider 2 points A and B. I go from A to B along some path 1 which is a reversible one, but then I come back from B to A along a path which is irreversible. So let me draw it this way. Okay, so this path 2 is irreversible. Now what I do is that, so if one of the paths is irreversible, that makes the whole cycle irreversible. Okay, it's a cyclic transformation. I went from A to B but came back to B at the end, came back to A at the end of the day, and therefore it's a cyclic transformation. So now what I do is that this whole cycle is now irreversible, so I'll use Clausius inequality with the inequality, like, because it's a irreversible cycle. So this would tell me that d cross q by t is less than 0. Cannot be 0 because it's not a reversible cycle. But now what I do is that I break it up into contributions from this path and that path. So that would give me let me just see. we just say let me do it this way, just to conform to my notation. Let me go from A to B along this irreversible path and come back to A along this reversible path. Then if I just use this inequality, what I get is A to B along this irreversible path of d cross q by t plus B to A of d cross q by t along the reversible path, which is reversible is 1, reversible is path 1. This is path 2, this is path 1, this is less than 0. But now what I can do is that I can bring this to the other side, okay, or A to B of path 2 of d cross q by t is going to be less than, if I bring this to the other side I get a minus sign, but since path 1 is reversible I can absorb that minus sign and make this into an integral going from A to B along the reversible path. So I get A to B along path 1, which is a reversible path of d cross q by t, and this quantity is by definition is B minus SA according to the previous statement, and therefore I have proved what I was after, namely that for an irreversible cycle d cross q by t, this change is going to be less than SB minus SA, and of course if it's a reversible path, if this is a reversible path, then I have an equality as I have shown previously. And also this thing allows me to prove this statement that if the transformation is taking place in thermal isolation, I mean the state of the system is changing, you start from an equilibrium state, you do some quasi-static transformation, doesn't have to be reversible, could be irreversible. I start from an equilibrium state, I make small changes, it goes from state A to state B, and while I am doing that, I don't allow the system to exchange energy with the external surroundings and exchange heat with the external surroundings, and therefore dq by d cross q is equal to 0. So I have a system in thermal isolation, you know, a transformation which is taking place in thermal isolation, then the left hand side is equal to 0, and therefore what I get is SB. So SA is less than equal to SB, or SB is greater than equal to SA. So if the transformation is irreversible taking place in thermal isolation, then the entropy of the system increases. The entropy of the final state cannot be smaller than the entropy of the initial state. Of course, if it's a reversible process, then the entropy remains the same. But if the process is irreversible transformation, the entropy increases, and that allows one to make this statement that for a thermally isolated system, the state of equilibrium, the state in which you keep on increasing the entropy, and therefore the final state will be the one in which the entropy has its maximum possible value. Of course, one doesn't know what that maximum possible value is, but it just tells you that the state of final state is going to be the one in which the entropy has got its entropy is maximized. For a thermally isolated system, the state of equilibrium is the state of maximum entropy, Maximum entropy subject to constraints. I mean, you cannot just maximize the entropy without taking care of all the constraints that are there. For example, the total volume of the system is whatever, the total volume of this chalk is whatever it is, and this is the temperature and so on. So, consistent with that, this is the definition of the entropy. Do I need to do anything else? So, Carnot entropy. So, there is this thermodynamic potential. So, what they can be introduced in a course on thermodynamics. I mean, one doesn't really need to invoke statistical mechanical idea, but what I prefer to do is that I will introduce those thermodynamic potentials, Gibbs free energy, Helmholtz free energy, while I deal with the corresponding associated ensemble, instead of telling about them right now, because then you see that there is a physical meaning to each of those thermodynamic potentials, and you also know how to compute them and so on. So, till now whatever I have talked about, you see that there is a missing link, in the sense that what you are given is, like, let's say you start from classical mechanics. In classical mechanics, what you are given is, you are given a system for which you build up a model, namely there is a Hamiltonian that you have in your hand and the Hamilton equations of motion. All these things don't tell you how to compute all these quantities, entropy, energy, heat, not just compute, you don't even know how to interpret them in terms of Hamiltonian and the equations of motion. It just doesn't tell you how to do that in terms of microscopics. Like the microscopics are these constituent particles, they are moving around in presence of some potential and some external field, and they have coordinates, momenta, etc. And they don't, this framework, it doesn't tell you, simply because it is not supposed to tell you, it's just based on some experimental findings. You see that certain processes don't happen in nature, and this is just a way to couch this in the language of some statements that okay, this is not happening, that is. So it's more or less the end of what I want to do with the thermodynamics. So please tell me if there are specific things that you would like me to cover. Like otherwise I move on to statistical mechanics. I'll try to make some connection to nonlinear dynamics and so on, but I mean statistical mechanics, in thermodynamics, besides, I mean these are really the main things, main topics that one should know about, and then one kind of derives a number of equalities, inequalities and so on. Mostly equalities, Cp minus Cv is equal to R, and this Maxwell relations and so on. But that's pretty much algebra. I mean, not much of physical concept is involved in doing. Carnot. I don't know how Carnot did it, but this is what Carnot was after was he was trying to construct an engine that will deliver the maximum amount of work possible out of this. He was trying to build a heat engine. So what an heat engine does is that there is some fuel or something, so it would burn that fuel, and it would get some useful work out of it by doing some thermodynamic transformation, and that work can be used to, for example, when you drive your car, that's what you do basically, that the fuel is burnt, and then you get some useful work out of it. I don't know exactly how Carnot did. It's a book in French. I mean, like as I told you, the name of the book is very interesting. Like you might find it interesting. The name of the book is what did I write? It's called Motive of I don't know what. Motive power or something. This one. It says Reflections on the Motive Power of Fire, 1824. This was his first. 1824. By the way, I just looked up. I used to think that Lagrange was a French person, but actually was an Italian. He worked in Paris, more or less.
Yeah, he was born in Turin.
Torino, Paris.
And Italians say he is Italian. Giuseppe Luigi
Yeah.
The French say he is French.
Joseph. So there is a.
As you say,
he lived in France. Okay, so anything that you want me to do, or I just start off with?
I want to our negative thing leads to a positive thing. Actually, you can think of the entropy. It is nothing positive. It is a measure of our inability. So in that way, you can think of entropy as something.
Well, at this stage, that interpretation of inability and so on is not there. Like that interpretation of entropy came, many years later. I mean, in terms of information loss and so on. And actually, it did not arise in the context of thermodynamics or statistical mechanics. From the information theory. So you want to make?
I was talking about Shannon's.
Shannon. So that was many years later, and that was in a completely different context. So at this stage, people did not know. Like they could have called it something else also. I mean, it doesn't have to be entropy. It could be. It just lets you define a function. And what Professor Mukunda was pointing out was correct. That how come you have a series of negative statements and then you end up with a positive statement. I mean.
just
Yeah, sure.
Suppose you say you should never spend more than you earn. And you should never eat more than you need. And you say at the end you get a statement. Therefore, in your bank account you will find so much.
No, but it is possible, no, that you should never, you should never drink, you should never party and so on. And so then I am forbidden to do several things in life. So end up saving a huge amount. Right?
Can you say exactly so much will be there in your account?
Perhaps, okay, first I have to.
Just something.
Yeah, sure.
And the other thing is, entropy is a very important concept for chemical engineering.
Yeah.
No question about
Yeah.
it. So they are not using it in the Shannon's.
Yeah.
They are using it in the old.
Yeah. I think for them probably free energy is much more useful, but it's derived from entropy. I mean, they always look at
what we call enthalpy.
enthalpy. H is U plus PV. Yeah. Enthalpy.
Aeronautical engineers.
Yes. So then shall I start with the statistical mechanics part? So that's going to, okay, so let me do that. So since I, so what I would like to suggest is that, I mean, since I skipped many things, for example, the proofs and so on, and in our library we have several copies of this Fermi's book. Okay, this also can be downloaded, I'm sure. So if you find some time, please go through the proofs, and they are very beautiful, and if something is not very clear and so on, so then we can discuss them in one of the tutorials. I mean, this could be a good way to make use of the tutorial session. Now let's start with statistical mechanics. Like as I said, your starting point is a Hamiltonian. So you are given a Hamiltonian. Okay. So first of all, you have n degrees of freedom, and let me call them n or 3n degrees of freedom. So what I am thinking is, let's say particles moving in 3 dimension or something. So you have 3n degrees of freedom. So these are the generalized coordinates, and these are the conjugate momenta. And they satisfy the Poisson bracket relationships that you have seen so many times in this course. And you are also given a Hamiltonian, okay, I was writing there, where this P refers to all these 3n the conjugate momenta, and Q refers to all these generalized coordinates. So can someone tell me what is n? N is the number of dynamical variables. So I can look, this is very much a dynamical system according to my definition of a dynamical system. So I should also write down the equations of motion, the Hamilton's equations. So it says Qi dot is equal to del H del Pi, and Pi dot is equal to minus del H del Qi, where I runs from 1 up to 3n. So just to make connection to my lectures on dynamical systems, so what is now n? N is the number of dynamic, 6n, right? And so we are going to deal with a situation in which n is typically very large, of the order of 10 to the power 23. In the dynamical system setup, n could have been anything, like it could be 1, 2, 3, etc. But here I have 3n, the total number of equations that I have is actually 6n. I mean 3n, half for the coordinates, for the generalized coordinates, and half for the conjugate momenta. And these equations are coupled to one another, okay? And they may be linear, they may be, typically they are non-linear. Non-linear first order coupled differential equations. And what I want to do, what I am after is the following, that in this setup, I want to understand the laws of thermodynamics. Like I want to interpret energy, internal energy, heat, entropy. I want to interpret those quantities in terms of microscopic variables like generalized coordinates, generalized momenta, Hamilton, and so on. The system Hamiltonian and so on. Okay. So the first concept is, so the setup is I have 3n degrees of freedom and I have an isolated system. So if I have an isolated system, then we have seen this many times, that the total energy is a constant of motion. You start out with some amount of energy, and as the P's and the Q's evolve in time, the total energy of the system is going to remain constant in time. It doesn't change as a function of time. So the first concept is the concept of phase space. Now I think it should not be very difficult for you to appreciate what it is, because I saw in the motivation letter of many of the participants that they all complained that they are very confused about what a phase space is. So what is a phase space? If you recall my definition of a phase space in the context of dynamical systems, I said that okay, it's a space, it's just a space whose the axes are the different dynamical variables. So there are 6n dynamical variables, small n equal to 6n dynamical variables. So these are the axes of this phase space. This is the gamma space. And what are the different axes? So this is Q1, Q2, Q3, and similarly P1. It goes up to Q3n, and then P1, P2, it goes up to P3n. And then in this 6n dimensional space, the state of the system, the microscopic state of the system, is denoted by a single point. Okay, so that allows, or that leads us to the definition of a microstate. So what's a microstate? It's the configuration of the system. It's the microscopic information about the system. I don't know what is the exact way of is there a, Okay, so what's a microstate? So microstate is defined by telling me, by giving you the values of all the n dynamical variables. So a microstate is defined by all the n or 6n p1. So that's a microstate of the system. This is the most detailed information that you can have about the system, that I have a system with 3n degrees of freedom, and therefore there are 3n generalized coordinates and corresponding 3n the conjugate momenta, and I give you the values of each of these 6n generalized coordinates and momenta, and that defines for me a microstate of the system. And a microstate is denoted by a point in this n dimensional. This is not a patch. This is just a point in this 6n dimensional phase space. That's a microstate. So a single point in the 6n dimensional phase space is telling you everything about the system. If you want to know anything about the system, you need to know the values of all the variables, and that's given by a single point in this n dimensional phase space. And we have already discussed that as the q's and the p's evolve in time, how is this point going to move around in this 6n dimensional phase space. The first thing, of course, is to note that since it's an isolated system and total energy is a constant of motion, so therefore this point is going to move on a 6n minus 1 dimensional hypersurface, because it cannot violate the condition that the total energy is a constant of motion, and therefore on this 6n dimensional hypersurface it is going to move around with the condition that a trajectory of this representative point cannot do like this. There cannot be any self intersection, because as we have discussed many times, since these are first order differential equations, and if I start with a given initial point, namely given values of the q's and the p's, then the future is determined once and for all, and therefore you cannot have an intersection, because at the intersection point you are going to have did I do it this way? Two possible future, one is going this way, one is going that is not allowed. Also, if you have two trajectories starting from two different initial conditions, they also cannot cross each other. So you cannot have a situation like this. There is a phase space trajectory starting from this point, there is a phase space trajectory, a different one starting from a different point, and then they cannot cross each other, because then you will have indeterminacy at this point of intersection. So these things are not allowed. So that's the definition of a microstate. So the next thing is the concept of macrostate. Macrostate is similar to what a thermodynamic state is. Okay, macrostate is a state defined by values. It's given by, or it is completely characterized by values taken up by certain macroscopic observables of the system, the total volume, the total pressure, temperature of the system, and so on. They have nothing to do with microscopic degrees of freedom. A macrostate is defined by measurable quantities that refer to the system as a whole. What is the total volume? How many particles are there? N is also a part of how many particles are there, what's the temperature, what's the pressure, and so on. So these are necessarily measurable quantities. Okay, it doesn't tell you how to measure them, but by definition these are measurable quantities that refer to the system as a whole. But microstates are not. You don't know how to measure them. Probably there is a way to measure them, but that's it. But now I make an observation, which is the fun.
Suppose I want to locate one more microstate on the same phase space. What should I do? Should I change the initial condition over here?
You want to locate one more microstate for same macrostate. Okay, so I am coming to that. This will be a very difficult thing to do, so I am coming to that. So is the distinction clear between the microstate and a macrostate? A microstate refers to the the coordinates and the momenta of each of the constituent particles of this piece of chalk, while a macrostate refers to just how much does it weigh, what's the color, what's the temperature, and so on, pressure and so on. It doesn't refer to the microscopic details of the system. So then you realize that if I tell you what the macrostate of the system is, there is no way to make out what's the microstate of the system is. There may be a very large number of microstates which are possible, and they are all consistent with the given macrostate of the system. If I tell you that the total length of this chalk is whatever it is, it doesn't tell you where each of the constituent particles is located at a given time. They may have many different possibilities, and they all could be consistent with the given macrostate of the system. So if you ask me how do I get a different microstate, I don't know, because this one macrostate, so you may think of it like this, that this one macrostate, so this kind of corresponds to many different microstates. There is a huge number of them. So they all correspond to the same macrostate. To put it differently, these all microstates, like all of these, are consistent with the given macrostate. I can. Yeah, this is not degenerate in the quantum sense, but.
Because so many microstates lead to the same method.
I don't know whether degeneracy is like energy. You think in terms of energy. In some loose sense. Okay, colloquial. I would be careful in using such a term like degeneracy. It could make it could lead to some confusion. That it might mean that well, all these microstates, okay, indeed they all have the same energy. Okay, in that sense, in some. Yeah, that's because it's an Yeah, I would not call it but okay, you got the point, that if I tell you the macrostate of the system, there is no way for you to tell me what's the microscopic state of the system is, or what's the microstate of the system is, because there could be a very large number of microstates, and especially so since n is very large. N is very large, and like had it been 1 degree of freedom, like then probably I could have said, okay, I could have. But then since it's this chalk consists of so many atoms and molecules, if I tell you the length and the temperature and the pressure and so on, there is no way to find out what's the microstate of the system. So all these microstates, they all are consistent with the given macrostate. So when I say that this is my system, there is no way for you to tell me which microstate the system is in. It could be at that particular instant, at the instant at which I am telling you, I am giving you information about the macrostate. At that particular instant, there is no way for you to tell me which particular microstate the system is in. So it could be either here or there or here, all these possibilities are possible. They are all consistent with the given macrostate. So this set of microstates, which are, I am not writing that, which are consistent with the given macrostate, is called an ensemble. Ensemble just means that collection. It's a collection, but it's not a random collection. I have to list down only those microstates which are consistent with the given macrostate. Let me give you an example of an inconsistent microstate. Let's say the length of this chalk is, or let's say the length of some material is 1 centimeter. And if I ask, if I give you a microstate that gives me 2 particles which are separated by 1 kilometer, It's a microstate, but it's not consistent with the given macrostate, because if the length of the chalk is 1 centimeter, then its two of its constituent atoms or molecules cannot be separated by 1 kilometer. It's a microstate in that sense that, you know, I am telling you, I am giving you information about the coordinates, but it's not a microstate consistent with the given macrostate. Okay? So this collection of microstates consistent with the given macrostate is called an ensemble. It was, I think Gibbs was the first one to coin this term, ensemble. By the way, this term ergodic that I was using yesterday, Boltzmann was the first one to coin this term, ensemble. Yeah, yeah.
The system must be macroscopically identical.
Macroscopically, there is just one system. Nothing. There is just this chalk is my. I am. You know, think of me as a system. Huh? There is just one system. In some books, they make this. You know, this might seem a bit confusing. They say, you know, set of all systems. Instead of saying microstates, they say set of all systems. It's not. System is just one entity. System is what is determined or what is defined by the macroscopic values of these measurable quantities. You tell me the height, the color, the skin color, the weight, this and so on, and that's my system. So there is just one system. So in some books, and I think in Carson Wong also, they call them you know, the different microstates are referred to as different systems. I think it's a bit confusing. They are not different systems. It's just one system. So the infinitesimally many microstates. Yeah. So okay, let me say this way. System. When I say system, as soon as I say there is a system, then I have to tell you what the macroscopic state of the system is, the volume, temperature, pressure, or you know. So suppose I take this as my system, then I have to tell you how much does it weigh and what's the density of this material and whether it is empty and so on. So that's my one system. Now this system is constituted of atoms and molecules, and they all form different possible microstates which are consistent with this. I think one should not refer to them as systems. I mean, they are not systems. They are just microscopic configuration, and instead of writing this big word or saying this over and over again, microscopic configuration, I call it a microstate. That's it. Okay. Identically prepared, I know, I understand why they call identically prepared, because you know they all refer to the same macrostate, but I think the notion is simpler than that. I mean, one doesn't necessarily have to bring in complicated, complications and so on. So I remember that in our school, just outside the library, there was this thing written somewhere that like, are you here with the solution, or are you yourself the problem? So in doing, I become the problem. I am supposed to give you the solution. I am trying to bring in more complication. So let's go back to this picture of this phase space. I hope this distinction is clear, right? Microstate and macrostate. And if ever somebody tells you identically prepared systems and so on, I think it's better to like avoid that. Or you know, if you understand the distinction between them, then of course it's okay. Then you can say that okay, you are fine.
Proceed with the question.
Huh? Conditions apply. You can say star conditions apply, as they say nowadays everywhere. You go to buy a ticket and say if 350, 3,500, and then star conditions apply. You can think of it that way. So there is some confusion. No, okay. I'll redraw this picture.
The coordinates correspond to first particle, second particle. Is it like that, or it is the number of independent variables?
You define for me the generalized coordinates. See, the particles, I can label them in my head, but the particles are indistinguishable at this stage. I can think of this as my first particle and second and so on, and if I can keep track of the labels, it's fine for me, but the system doesn't behave that way, that all the particles are indistinguishable. These are classical particles, they are indistinguishable. So I can think of them as, let's say if I take a one dimensional line and then I know that the particles cannot overtake one another, then probably there is a way to like label them, and then that if I label the particles once at t equal to 0, that labeling is going to be preserved in. This is my first and second and so on, but the particles are all the same. So there is no distinction between the first and the second particle.
Constraints are incorporated. Constraints are also incorporated.
Yeah, the constraints, because these are degrees of freedom. So yeah, it's not good to think of them as kind of the degrees of freedom. Many particles. There are n degrees of freedom. I said no, there are 3n degrees of freedom, where n is 10 to the power 23. Think of the chalk. This is a good example, because I think in your class you use a chalk to write. So this is unless you are using these board markers and so on. So you can use those as also examples of a macroscopic system, because a macroscopic doesn't necessarily have to be the whole galaxy. I mean, it could be like anything whose dimension is much bigger than the molecular dimension. Doesn't have to be big.
Does that point in the phase space give any information about the number of particles?
Well, you have to count the number of axes that you have. It's all in your head. Like this construction, this phase space construction is just a convenient construction to help you think about how the system is going to evolve in time. Okay. Of course, the number of particles, or let's not think of them as particles, or you can think of them as particles also if it helps you, but the number of degrees of freedom is going to tell me the number of axes that are going to be there in this phase space. But I don't know a way to count the number of axes, so to say. And this microstate, like as I said, there is no way in which I can measure the microstate of a system. The only information that I have access to is the macrostate of the system. I can do some measurement, I can find out the temperature, pressure, volume, etc., susceptibility, this, that, okay, and that I can do, but there is no way to find out the coordinates and the momenta of the individual particles inside this chalk. So I was going to draw. So what's the next thing that I should do? Okay, so this is my phase space, and this is one microstate, and I told you that this microstate is going to live on a 6n minus 1 dimensional hypersurface. Okay, so it's somewhere there. But I also told you that if I give you information about the macrostate, that doesn't tell me anything about the microstate of the system. So if at a given time I give you information about the macrostate, there could be a very large number of microstates consistent with the given macrostate, and I can think of representing each one of them by a point on this surface. I don't know how these points are distributed, where they are, but I know for sure that they are going to lie somewhere on this 6n minus 1 dimensional hypersurface. I don't know how to find them, where they are, but I know that they exist for sure. I don't even know their number. What is the total number of microstates? That also I don't know, but I know that there will be quite a large number of them, and they are all going to live on this 6n minus 1 dimensional hypersurface. How will it? Yeah, but so you have to. If see, okay, look at it this way. You want to derive or extract some information based on the information that I am giving you. I am telling you that look, the weight of this thing is this much, and the color is this much, and the susceptibility is this much, and this is magnetized, the magnetization is this much, and so on. On the basis of that, you cannot derive or extract such information. It's like I am not. Something could be possible in principle, but just on the basis of the fact that I tell you the macrostate of the system, it is impossible to pinpoint which particular microstate the system is in, just on the basis of that information. So at a given instant, suppose you take a snapshot of the system. A chalk, I keep referring to chalk because chalk is a very good example. Suppose you take a snapshot of this phase space. So you see that all these points are distributed in some way or the other, consistent with the given macrostate. Like for example, in the spatial, in the spatial direction, that none of the points are going to go out of the actual spatial dimension of the chalk. It cannot be that one point is here and the other point is at Belur Math when I am referring to a chalk. It's not possible. It's a microstate. It may lie very well on this hypersurface. Because this hypersurface extends all the way from wherever you are coming from, South India, all over. This is an infinite plane. It could be that I get a point here and one point very far away. That's a microstate because it's lying, but it's not consistent with the given macrostate. So I am referring to those microstates, the collection of those microstates which are consistent with the given macrostate, and this collection is called an ensemble. By the way, I keep saying this in my class. Probably it is just I am just being too much fussy about trivial things. So it's a French word which is called ensemble as opposed to ensemble. You can call it ensemble, probably it doesn't matter, but I am just used to calling it an ensemble. Andrew, all this entrepreneur. So the en is always on. I don't know, like there must be many friends. But entertainment is entertainment. It's not entertainment or something. Okay. So now that you have this collection of points on this hypersurface, and you don't know where they are, how they are distributed, I should think of a way to characterize this system. Characterize this collection of points, that there is this hypersurface and these points are distributed on the hypersurface. So how do I, I might think in my head that it could be that points are crowded towards maybe the periphery. They are not so much crowded near the center and so on. That's a trivial, or maybe like everywhere they are uniformly distributed. These are the usual terminologies that we use, right? And as soon as I say that they are crowded, they are not so crowded, so at the back of my mind, somewhere I have this notion of a distribution. How are they distributed in time? It's just think of a crowd. You go to one of the train stations and so on, and you take a snapshot of the railway station, maybe the Howrah station or wherever you come from, and you take a snapshot and you see that at some places people have there's a large number of people there discussing something. So you take a snapshot to time, you freeze the time, you see that some parts are more crowded than others and so on. And it's natural to, as soon as you say that it's more crowded, less crowded, somewhere at the back of your mind you have this notion of a density. How many particles are there in this unit volume? How many particles are there in this unit volume? In unit volume. Why do you say unit volume? Because that gives you, there is no point in saying how many particles. If you say there are 50 particles, if you just make a statement, there are 50 particles, it doesn't make any sense, because I have to tell you the amount of space where they are occupying. A natural way to say is that how many particles are there per unit volume or area or something. Suppose I tell you, there are 50 persons in this room. It doesn't make any sense. I have to tell you, the density per unit. If I tell you just 50, I have to also tell you the total amount of space that are being occupied by them. No, phase space is microstates. Microstates. The number I don't know. No, it will not tell me. It will not tell me. You have just a point. It will tell me in this construction is in my head. So it will tell me in one way, in the sense that suppose I had a way to find out how many components are there. If you have a point here, so that's a vector that connects from the you can think of a vector that connects this point from the origin, and if I had a way to find out how many components are there, then I could have told you that okay, these many components are there. But as such, so think of only the macroscopic the macrostate as the measurable thing. This microstate I don't have an information of, and there is no obvious or easy way to find how many particles are there just by looking at microstate. There could be other experiments that I am able to do, but not and in fact I should be able to tell you the number of particles, because that information goes into defining the macrostate. So let me just make this correction, that I should be able to tell you how many particles are there, but not by looking at the phase space. I construct this phase space like after I have all the information of the macrostate. So the first thing is to identify the system of interest. What is my system of interest? It could be this one, my watch. It could be this one. This is my system of interest. Now I have to tell you, define for you the macrostate. That it seems like the temperature is around 25 degrees centigrade, and I think it has in 1 mole 10 to the power 23 atoms and molecules. I tell you this information, then I construct it should not be the other way around, that I have the phase space and now I start making measurement and then I tell you, oh, the number of particles is this much. It is not possible simply. Okay. So like as I said, there are these points, I mean they are distributed in some way over this hypersurface. I don't know how they are distributed. Now the question is, how do I characterize? Typically you would say that maybe some points are crowded here, crowded there and so on. So naturally at the back of your mind you are thinking of a density. How many particles are there in a unit volume? So let's define that density, accepting that I have to be careful now that I have a phase space which is 6n dimensional as opposed to 3-dimensional phase space, 3-dimensional space of the railway station. So what I do is that these are my, so I am going to use, if I use QP, this thing, then by Q I mean the full set. Instead of writing these things like over and over again, I will use this notation. Okay. So suppose I want to know how many particles are there at this location QP. And mind that Q has got 3n components and P has got 3n components. How many points are there? Are there like any point at all, or maybe the density is very high there? So how do I go about doing it? What I do is that I draw a small volume around it, and I ask how many points are there in that volume. Okay. So this allows me to define a function. So let me first name, so it's called the phase space density. Oops. So this rho is a function of where I am making the measurement. It is defined such that rho PQT dp dq, where dp, by dp what I mean is dp1 up to dp3n, and similarly dq means dq1 up to dq3n. This is by definition the number of phase space points, I am not writing it, number of phase space points contained in a volume dp dq around the point pq. I heard dp dq and something is unclear, or okay. So this is my definition. So how do I construct that? If somehow I had a way to scan the phase space and find out how the points are distributed, then what I would have done is that I choose a point where I would make my measurement or my observation point, and then what I do is that I make a small volume around it and I count the number of points which are there. I divide out by the volume of that element, and that if I divide out, the number that I get is rho PQT. This is the density, number per unit volume. Okay, excepting that you have to remember that it's a unit volume or a volume in this 6n dimensional phase space. So dp dq, it doesn't have the dimension of length. Q doesn't have, Q could be theta. I mean, like we have discussed it so many times. So you have to take it with that pinch of salt, that it's not quite really a volume in the traditional sense of length cube and so on, but it could be. But PQ has the dimension of h bar, the Planck's constant. This is for a given macrostate. If at a given time at 350, I tell you this is the length, this is the volume, and at that given instant, I can construct this function in principle. In practice, I won't be able to do it, but in principle, I can construct. So what I have to do is that, or I can construct these functions, let's say for simple like Ising model and so on, which are of course systems involving discrete variables. So what I have to do is that given the macrostate, I make a list of all the possible microstates which are consistent with the given macrostate, and in principle I can do this. On a computer, probably for simple systems you can try this, but one doesn't have to, because we will see that we are not going to use this function as such, we are going to use certain properties of this function. So now let's ask the following: why there is a time dependence, or what are the possible sources of time dependence? So one source of time dependence is the following, that suppose I freeze my time, but then if I move to a different point, I am going to see a different density. Okay, so that's why there is a dependence on P and Q. That's one. And secondly, like even if I don't move around, I just stay put and let time pass by, then of course, as I stay at this point, I mean, like as I stand here at this point, some points, because each of this phase-space point is going to like evolve in time, right? Each phase-space point will evolve in time following the Hamilton equations of motion. Okay, so each microstate is evolving in time, and therefore, like even if I stay at one point, as I am doing here, it might so happen that in this unit volume, some points enter, some points leave. So there will be changes in the number of points that I measure to be there in that unit volume. So there is a time dependence, explicit time dependence there, or there may be an implicit time dependence, because P's and Q's themselves depend on time. And I would like to know, how does this function change as a function of time? And that I claim is rather easy to write down, because I know how P's and Q's change as a function of time, and therefore I should be able to write down an equation for how P's and Q's change as a function of time. So let me just write that down and probably leave it at that. So this equation is actually, we have seen, so please remember that this is an example of a conservative system. So if I have a volume element in which there are 50 points, and I ask, how is this total volume going to change as a function of time? It may get distorted and so on, but the total volume is going to remain the same. So some points may come in, some points may go out, but the total volume cannot get changed as a function of time. So a different way to put it is this. This is another version of the Liouville's theorem. L-I-O-U. So O-U. Sir.
Because already there is an implicit dependence of time over all microstates. Should I consider that dependence of time for the rho as well? Is it necessary?
Yeah, it is necessary, because like even if you
all possible
so but no, what do you mean by already like evolved? You are taking, you are looking at the picture instant by instant. You are looking at the phase space instant by instant. Like even if you, like even if you don't change your observation point P and Q, if you stay at one point, you decide not to move, but the points are passing by. So then at different instance you are going to record a different value of the density. That's natural, right? Because I have at a given instant, if I move to different points, I am going to record a different value of the density. Or at one location I don't move around, but I look at I let all the microstates evolve in time, then of course these points are moving around following the trajectories. So like even if I don't move, there is an explicit time dependence, right? The points are moving around. I don't know. Okay, so let me tell you how to show it.
Given instant of time, there will be only one point, because entire system is represented by one.
No, at a given instant of time, there are many points. You don't know which microstate you are in.
It's okay, but anyway, it has some set. It has some values of Q's and some values of.
I don't know which one it is.
But it may be something. Then at another instant, it will be another line.
No, so see, the way to see it is the following. You are trying to construct a picture based on the information that I have given you. It's not that I am able to do this, I am able to do that. You are saying, okay, I have a way to find out which microstate I am in at a given instant, and then of course all this thing you don't need to like invoke any of these. You know which system you are, which microstate you are in, you just evolve according to Hamilton equation summation, that's it. It's just one point which is evolving in time, that's it. But you are not, that's not what I am trying to do, okay. So it's like, you have access to some information, you are trying to construct a picture based on that information. What information did I give you? I did not tell you what the microstate could be, or what I am telling you is this is the macrostate of the system. This is the total length, this is the density, temperature, etc. Now I let you do your own thing. Then you think in your mind that look, this is a macrostate, but I don't know which microstate the system is in, and I don't have an obvious way to find out which microstate the system is in. So let me just list down all microstates which are possible with the given macrostate. It's quite a natural thing to do, right? That suppose you are given some gross information that look, this guy lives in Calcutta. So you think in your mind, okay, he lives in Calcutta. Okay, so it could be that he lives in Belur Mutt, maybe in Salt Lake, maybe in I don't know. These are the only
places.
These are the only places where I have access to. No. I'm just saying. Maybe. So what you do is that you make a list of all microstates. But a microstate cannot be. If I say, oh, this guy lives in Calcutta, it cannot be, oh, this guy lives in Mekri Circle, for example. This is Mekri Circle is in Bangalore, close to. This is a microstate, but this is inconsistent with the given macrostate, because the given macrostate is the person lives in Kolkata. He cannot, that microstate is not possible.
So I think you can say you must take the idea of an ensemble.
Yes, exactly. Ensemble is the way to look at it, because this is the only thing that you can construct based on the information that I have given you. There could be.
It is constructed, okay?
It is constructed. It is
There are so many points. Now we have pointed out all possible microstates.
all possible
Now
microstates.
there is the question of moving the points.
No. The moving is the following. That at a given instant, I have constructed all possible microstates and I have put them on the phase space. Now, as time goes by, these points are not going to stay put. They are going to move around. Each point is going to move around because the microstate is evolving. P's and Q's are dynamical variables.
You cannot forget Hamilton's equation.
Yeah, you cannot forget Hamilton's equation. And statistically, in fact, my aim is to be able to derive thermodynamic laws based on the Hamilton equations. That's why I had written down those Hamiltonian equations in the first place. I cannot, like as Professor Mukunda, I cannot forget about that. At a given instant, these are my microstates. I don't know where they are, but I have enlisted all of them and I have put them, represented them by points on the. But time is flying. Now it's 2-3 minutes. So these points are going to move around in some way. The way is dictated by Hamilton equation, not in some way. They cannot go around in some way. Consistent with the given macrostate, of course. The total, so okay, so that it's a good point to probably stop. The total number of microstates is going to be conserved in time. It cannot be that newer microstates get created or microstate disappear. The total number, once I have listed down, a simple, let me give you a very simple example of it's not easy to, you don't know this, no, probably this Ising model, probably it's not so well known, so forget about it. So for a given macrostate, I have listed all this, the number is conserved. And now I am asking, how does this rho change as a function of time? And we will see that it changes as a function of time following what is known as the Liouville's equation. Let me just write down this equation and leave it at that. Del pi, or no, let me put it in terms of this Poisson bracket here, which is probably the best thing to do. So this is equal to, well, let me just check the sign. Is it okay? With a minus sign. Okay, del rho del t is this is what I am going to prove in the next class. But since you have a free afternoon, okay, you can move around consistent with the macrostate. Then you have to come back tomorrow anyway. But please, it's not so difficult a concept to grasp. I mean, often in books they write it in a very, this identical systems, mental copies. I think one doesn't have to invoke those things. If you want to invoke, you can. But this thing is much simpler than what. I don't know, like, it is a good place to. Carson Wang uses this language of identical systems and so on, which I don't quite like. Okay, Landau is of course, but Landau may not be, may be difficult for some people to follow.
There is one caution I would say that this is a classical treatment. We can't speak of the number of microscopies.
Okay, yeah.
All the variables are
Yeah, that's also true there.
Loose way of
Yeah. Cannot count them actually. Well, that's why I wanted to give this example of an Ising model where you can do some counting, but then since people don't know, that's a quantum system anyways, I mean.
But I think in this class there has been enormous amount of discussion.
Yeah, which I am very happy about. I mean, that's one of the objectives of a refresher course. That so there is a very nice, I don't know how many of you understand Urdu or have a flair for this language. So there is a very nice शेर in a couplet. It says, चमन में इख्तिलाते रंगबू से बात बनती है, अगर हम ही हम है तो क्या हम है, अगर तुम ही तुम हो तो क्या तुम हो. That in the garden you need both the fragrance and the color to make up the whole thing. अगर हम ही हम है तो क्या हम है. It doesn't. अगर तुम ही तुम हो तो there has to be interaction. Like otherwise it doesn't quite work out. Yeah, so that so please do ask as many questions as you want. So it's good to degrees of freedom. Yeah, but degrees. Yes. Yeah, please have a look at this book, which I keep on referring. It's one of my favorite books, actually. Very, very well written. Yeah.
Can we take it or look at here only?
You can go to the library and you can, or if you want to borrow, this is library copy. If you want to have a look, you can take it